Inspired by EY's vision, Team 1 is here to pioneer tech solutions for hurricane challenges. Hurricane destruction is a recurring event in the United States, with an average of more than 10 named storms each season. Moreover, global warming is increasing both the likelihood and magnitude of hurricanes, and by 2100, the frequency of hurricanes in the United States is expected to increase by 60%. Between 1988 and 2019, the US climate disaster have resulted in a total approximate cost of damage of $2.6 trillion, and more than 80,000 people died, mostly indirectly from hurricanes and lesser tropical cyclones in the United States. Additionally, multiple after-actions reviews have identified inefficient governmental post-hurricanes effort during both Hurricane Katrina and Maria. Hence, the question is, how can the post-hurricane cost and the indirect death of the hurricane disasters can be reduced? Our solutions to these challenges is to leverage the power of computer vision. By creating an object localization model, we can effectively classify damaged and undamaged residential and commercial buildings. The data we are taking will be from the 2017 Puerto Rico Hurricane Maria and will be used to train the model, and the data will be gathered from two primary sources. The moderate resolution satellite data. This data will be used to identify challenges in vegetation and aid in identifying severely affected areas, and the high-resolution parachromatic satellite images before and after the Hurricane Maria. This data will be used to classify building types and conditions in the affected areas.
Forecasting hurricane-affected areas is challenging due to changing weather patterns and inadequate forecasting models. Accurate damage assessment requires high-resolution satellite image to distinguish between hurricane damages and pre-existing conditions. Effective management of varying image sizes and rapid analysis of post-storm photo sets are necessary for accurate damage assessment. Differentiating between pre and post hurricane environmental conditions is crucial for determining the full extent of damage and focusing aid of reconstruction efforts.
The NDVI analysis is excellent at detecting changes in vegetation, but its use in urban areas is more limited because cities by nature have a low NDVI variance due to roads and buildings. With this in mind, we have identified the following key areas of interest. The first area of interest is the northern shoreline, specifically Punta Salinas and Comunidad Palmas Park, which have residential neighborhoods to the west, east, and north. Furthermore, there's an industrial area south of Comunidad Palmas Park. These areas are suspected to be affected due to its closeness to the sea level and to the shoreline. The second area of interest is the east-western going ridgeline to the south, specifically the area south of Sabana and Sector El Punto, as well as La Macasa Forest Park. These areas have small clusters of both residential and commercial buildings, and they are expected to be affected due to their high altitude and north-facing location on the ridgeline.
Great. Now let's actually dive deep into our model results. We built a YOLO V8N model for detection, classifying the four building types Lidia introduced us to. At the top, you can see the results for the training data. At the bottom, the results for the validation data. We can observe that not only the classification error, but also the box error significantly decreased with each new epoch. Also, the precision scores and the recall scores have significantly improved over the iterations, thereby identifying our model as a pretty good model with, at the end, with 49 epochs and mean average precision of 78%. When looking into the confusion matrix, we can observe that we predict all building types. In particular, we are very good identifying undamaged residential buildings, but also all other building types, undamaged commercial buildings and the damaged residential buildings and the damaged commercial buildings. The last class, though, we do have some struggles, as we can see that there is quite the disturbance to also predicting the damaged commercial buildings, right? As we do sometimes predict it, but it is actually background. And that is given due to that in our dataset, some buildings are so heavily damaged that the model takes sometimes background as damage and vice versa, and thereby we have some sort of overfitting problem, but all in all, a very, very good score. Also, if you look into the pictures on the right, we are predicting all building types pretty accurately.
Business insights and recommendations. Our first insight revolves around the NDVI's critical role in showcasing the environmental resilience and recovery post-hurricane. Through our analysis, notably in areas like Punta Sanilas National Park and Comunidad Palmas Park, we have observed how NDVI values fluctuate before, during, and after Hurricane Maria. This not only underscores the immediate impact on vegetation, but also highlights a path to recovery, showcasing nature's resilience. Our recommendation: to harness these insights for strategic urban and environmental planning by identifying and protecting key vegetated areas and integrating green infrastructure within urban planning, we can bolster our ecological resilience. Moreover, establishing continuous NDVI monitoring and engaging communities in conservation efforts can significantly aid in our disaster mitigation strategies. Moving on to our second insight, the indispensable need for diverse data in crafting robust damage assessment models. Our findings indicate that expanding our dataset to cover a wide array of damage types and conditions greatly enhances our model's sensitivity and adaptability. This approach is crucial for capturing the full spectrum of hurricane damage. Now, to leverage this, we propose the creation of a comprehensive hurricane damage repository. This involves collaborative efforts to collect annotated satellite images, incentivizing data sharing, and standardizing data annotation. Such a repository would not only improve our model's performance, but also serve as a valuable resource for future disaster response initiatives. Lastly, we have recognized the critical role of advanced pre-processing techniques in enhancing damage detection. By refining satellite imagery through atmospheric correction, spatial filtering, and image enhancement techniques, we can significantly improve our model's accuracy, especially under challenging conditions. So, our recommendation is to develop an integrated pre-processing and analysis platform. This platform would employ state-of-the-art algorithms and machine learning to automate pre-processing, ensuring optimal input for damage assessment. Coupled with a real-time analysis capability, this would enable rapid, accurate assessments crucial for effective emergency response.
And that's it. Let's hope, in case there's another hurricane in Puerto Rico, the disaster recovery management will be more efficient now due to our research. Thank you for listening.